Hello, everybody. So then now that you have a basic idea of what we mean by a linear transformation, it's a mapping that in some way preserves linear combinations. It has those two properties that guarantee it. I've given you at least three examples of linear transformations between different spaces. And then I gave you two examples of how to show by counterexample that a mapping is not a linear transformation. It'll still be called a transformation, but it's not a linear transformation. It will not preserve linear combinations. So there's a bunch of properties, though, that have to be true for all linear transformations. And unfortunately for us, since the transformations are not defined by matrix multiplication, they're not really obvious anymore. I have to somehow convince you they are true just by the properties that you know. I'm going to prove only one of them because it's so easy to do all of these. I'm just not interested in doing them all over again. So for example, if you take the transform of the zero vector in V, you have to get the zero vector in W. Why? Well, because if you take the transform of the zero vector, that's the same as saying take the transform of the scalar 0 times any vector in V. But because T is a linear transform, that scalar 0 comes out to get 0 times the transform of V. But the transform of V is just some vector in W. So then 0 times that is the zero vector in W. And that's it. That's the proof. So that's nice that the transform of the zero vector in V becomes the zero vector in W. And actually, that particular property, one of the reasons I actually proved it for you, it's really nice to go and use it first. So remember how I showed you that you have to sometimes have to guess if a mapping is a linear transformation or not, and you look for counterexamples. Almost always this is the first one you want to draw, because if it is a linear transform, then the zero vector has got to be mapped to the zero vector. In fact, my previous example, when I went from the polynomials of degree 3 or less into the set of polynomials degree 3 or less, where the mapping was just return the function and add 1, that mapping, if you take t of 0, you get 1. You don't get the zero vector back. So then that mapping could not have been a linear transformation because it violates this property right away. Okay, so then there's some other tricks of the trade that you need in order to become more familiar with how to look at linear transformations. Suppose you have some mapping out there. I don't know, I'm not going to tell you what the whole mapping is now, though. The linear transformation of 1, 1 is going to be the vector 2 plus x squared. And the linear transformation of 1, 0 will be the vector 3 minus 2x. Based upon this, you should now be able to compute t of negative 1, 2. Now, your first thought would be, well, but you didn't give me the general rule, so we can't do it. Notice, though, that the vectors I gave you, 1, 1 and 1, 0, are actually a basis. They're a basis for R2. Every vector in R2 can be written as a linear combination of those two vectors. So if you look at it, the vector negative 1, 2 is the same as saying it's 2 times 1, 1, and then you're subtracting 3 times 1, 0. Right? That's correct. So if I want to find the transformation of negative 1, 2, it would be the transformation of that linear combination, but the transformation distributes right through everything because it's a linear one. You're assuming it is. So it'd have to be 2 times the transform of 1, 1 minus 3 times the transform of 1, 0. And we know what those things are. That would then be 2 times 2 plus x squared minus 3 times 3 minus 2x. And you're welcome to go ahead and just add that up. Notice this is a sneaky little trick. It seems to imply that if we know how the transform acts on a basis of the space, we know how the transform applies to everything in the space because it preserves linear transformations. All right, so then using the same kind of trick, you can actually also show that there is no linear transformation that would have certain mappings. So let's suppose you have a transformation that goes from the set of polynomials to the real numbers. So then t of 1 plus x is 1, and t of 1 minus x is 2, and t of 4 plus 2x is supposed to be 3. I'm going to convince you that that can't be true. That's impossible. It might be a mapping, but it can't be a linear one. So why? Once again, notice that 1 plus x and 1 minus x actually makes a basis for all polynomials of degree 1 or less. And that's what this is. So I can write 4 plus 2x as a linear combination of 1 plus x and 1 minus x. It's just a matter of finding out the right combination. Actually, here it's 3 times 1 plus x, and then you'd have plus 1 time 1 minus x. So the transform of 4 plus 2x would have to be 3 times the transform of 1 plus x, and that'd be plus the transform of 1 minus x. But the left-hand side would be 3. That would then equal to 3 times 1 plus 2, and that would be 5. And that's clearly false. That's impossible. They can't be equal to each other. So there is no linear transform where this would be true. And I believe that's enough for that video.